Hi, my name's Victor, and we are discovering the DFT together. Last episodes we talked about signals consisting of a bunch of sine waves, and also what happens when we multiply signals together. This episode we are puzzling all the pieces together to make the discrete Fourier transform finally happen. Are you excited? I am, I must say. Okay, anyway, I will demonstrate it with the program that you can get in the description below. Just look at the GitHub link. Okay, let's go. Let's look into the software. Okay, first of all, we have this DFT tab. When we click on it, there's a whole other page that opens up to us. Well, there's a lot of things over here, but let's not get overcomplicated. First of all, let's turn off all these things here. We don't need them for now. But now you will see we have another generator right here in the input section. And we have a window shape, which we will look at later, and also a test frequency, which we will also look at later. So first of all, let's simply look at the generator. Let's turn the knobs. Nothing happens. Well, in this case, the generator works differently. You have to look at the play and the skip and the separate knobs over here. If you press the play button, the generator starts generating samples. So let's see. You can see it generates samples. If you wanted to produce samples faster, you can simply turn up the sample rate and it will play them faster. That's wonderful. Also, you can pause the sample production and you can also skip through it, which gets quite handy in a second. Okay, so let's look at the test frequency. As we already said, the test frequency basically is a frequency with which we will multiply our input signal. So, but we want to sweep the test frequency through the whole spectrum and multiply it with the input signal and then look at the average. So instead of sweeping one test frequency around, we have simply 40 test frequencies from 0 to 39, and also always as a sine part which is straight in phase, and a cosine part which starts a quarter of the period earlier. Let's look at the multiplication window, and we will see how it looks like when they are multiplied together. Okay, so we get the same thing we already had, because at this point we have the generator making a frequency of 1, and it's being multiplied with the test frequency, and we get exactly the thing that we already talked about in the multiplication section. So now we could calculate the average. Actually, for continuous signals, it's pretty complicated to calculate the average of a signal. But we are working with the discrete Fourier transform, so we are looking at discrete signals. That's why we don't really need to look at these complicated integration functions things. We simply can add up all the elements and divide it by the amount of elements that we have added up together. That's the typical way of calculating an average. Okay, so we can see that in the spectrum down below. Let's, for example, turn on the sine graph. In this case, you will see a peak at the here in red. The sine spectrum is shown here in red. So when the input signal is perfectly in phase with the test frequency, we get an average offset, and this is displayed right here. When we're going like here, this is mostly centralized around 0, so we don't have a very big peak at this sine part of the test frequency. But when we play it further, now they are perfectly out of phase. This goes into the negative, and we have a positive peak here again, because this is the absolute value. It doesn't matter whether the average here is positive or negative, we will always have a positive peak. Okay, so let's look how that looks. So interestingly, when you look at it, the sine frequency the sine part, so the average of the input signal multiplied with the sine part of the test frequency, oscillates up and down when the input signal goes through. Now we can also turn on the cosine part, and you will see that the sine part and the cosine part oscillate up and down in an alternating way. We can also look at how the test frequency, the cosine part of the test frequency, multiplied with the input signal looks like. It looks like this. It does basically the same, but offset in phase. For example, let's stop right here. We are at the sine part. Every time the sine part is perfectly offset, the cosine part is pretty much centralized. You can see that right here. The cosine part is rather low, and the sine part is pretty high in average. This average is pretty offset. Okay, let's skip ahead and see what happens. When we skip to about this point, when the sine part centralizes around 0 again, the cosine part has an absolute offset right here, right? And so these alternate up and down when we press play right here. Okay, and now get something to hold yourself on, because now we are putting all the sine spectrum and the cosine spectrum together with this wonderful formula that is displayed right next to me. I don't know, due to the power of After Effects, I don't know. Right here you see the spectrum now in green. When I turn off the sine and the cosine, you can see that the green peak stays constantly at this level. Well, that has to be, of course, because the amplitude of the input signal doesn't change. So the amplitude of that frequency has to stay the same. Okay, and now let's slowly sweep up the spectrum and let's see how the spectrum gets reinterpreted. As we sweep the spectrum, using pressing Alt to make fine adjustments, by the way, the little peak wanders up. Isn't that beautiful? I don't know. I was very excited when I saw this, when it worked the first time. I hope I can share my excitement right here. Wonderful, isn't it? Okay. Anyway, let's put this back to maybe 3 or something, using Control to snap 2 values, and let's do it again. And now you see we have a perfect peak at 3. That's beautiful. So when we sweep through the test frequencies, we should see, yeah, the first test frequency, this looks pretty much 0 centralized, right? Then the second one looks quite centralized. And the third one, this has this oscillating average that goes up and down for the sine frequency and also for the cosine part of the test frequency. And then for the fourth one and the fifth one and so on, it centralizes at 0 again. Isn't that beautiful? Okay. It's always really important also to go to the extremes. Like, for example, the 0th frequency. What is it exactly? Why is there a 0th frequency? What does that mean? There's like 0 periods per this window? Well, that's absolutely right. The sine part of the 0th test frequency also starts at 0, and because there are no periods in the window, it stays at 0 all the time. And the cosine part starts at 1, as all the others do also, but it stays at 1 because there is no period at all within this window. 0 times any value of the input signal gives us 0 all the way for the multiplication graph. Okay, but for the cosine part, we have only once the whole window through. So 1 times anything gives us the exact thing that we multiplied 1 with. So we get the exact input signal right here. So we are basically calculating the average of the input signal right here. So when the input signal has an average higher or lower than 0, we will have a peak at the 0th frequency. Let's try that out by making the frequency like 0.5. Now it looks like this, and suddenly we get a peak right here, right? At the 0th frequency. Yes, of course. Here we can see the average totally goes below 0. There's a bunch of other things to try actually. It's so exciting, this thing. I played with it hours, but I won't show all of them in the video. Just grab the software yourself and try them out. You could try, for example, not only testing a sine wave, but a triangle wave or a square wave or a saw wave, however you like. And you can look at the spectrum and how that looks. You could maybe also play with noise and look at what kind of spectrum noise gives you. There's also one other option right here that I haven't touched yet. You can enable the window shape, and with the window shape you can also draw a window shape how you want the multiplication to be shaped again. Like for example, if we set all this area to 0, there's nothing in the multiplication section because all of these values get multiplied by 0 too. So you can shape this, and you could also make the window shape smaller and look at how that affects the frequency spectrum. You could shape the window a bit smoother and look whether you can gain any precision. Also, if you wanted, you could try out inputting a delta pulse. A delta pulse should contain every single frequency. Try it out whether that gets you this exact result. You could also produce one signal with a generator and then pause the sample production and quickly change the frequency and then resume the sample production and watch as the spectrum gets reinterpreted. So what else can you try? Give us some inspiration in the comments below. Try out yourself and see what you can come up with. Frequency analyzers basically do the same thing. They capture the last few samples of the audio that is passing through, and they calculate the spectrum based on these samples. They also check every single frequency. But frequency analyzers do a bunch of things differently than my program right here. First of all, they have a smoother window shape, and this allows them to test more frequencies, but gain more precision while testing. Also, they don't calculate the sine and the cosine part separately, but they do something that's called a z-transform or a z-transform, however you want to pronounce it, which involves complex numbers and is a whole other topic for another time. Another difference is frequency analyzers are typically scaled logarithmically in both ways. So the frequencies are scaled logarithmically, and also the amplitude is scaled logarithmically, as it is often given as decibels. Okay, what else differences are there between my program and a frequency analyzer? I'd be curious to know. I can't really think of anything more, so post it in the comments below if you can think of something. There's one last thing that we have to discover. Remember how I said you have to push every knob to the extreme? Well, there's one specific knob that will produce some interesting results when we push it to its extreme. Let's look at the frequency knob. Okay, so right now we have a frequency of let's say 18, and we get a peak at 18. Makes total sense. Okay, let's push it further, and we will see the peak is rising as well. That makes sense. Okay, right. But we can see that this frequency spectrum only goes to the frequency of 39. What happens if we push the frequency beyond that? Let's do so. And now the peak goes back down, even though I pushed the frequency up. That is surprising. When I push the frequency further, the frequency wanders back down. all the way. That is really interesting. Well, this is called aliasing. This happens because in this case we have a window that is filled with 80 samples, and we can only test up to half the amount of samples that we are looking at. So we can only test up to the frequency of 39 right here. That is interesting. But why does that happen? Aliasing, the Nyquist frequency, and why we are confined by this frequency range in which we can test a given signal will be the topic of the next episode. Look down in the description below, the whole series is linked there. Okay, bye. Have a nice day.